This is Mrs. Palmer-Quay with the first quarterly test review. The test will include both concepts that you have already been tested on in the quizzes, just as a way to check that you really know this stuff, and certain problems that have been part of the textbook homework. I know I've not been grading the textbook homework, that's been left up to you and your parents, but you should be doing the review questions and the practice problems, and certain of those practice problem calculations will be found on the test, but it all will be covered in this video so that you will know what to study. First, let's start with significant figures. Remember that significant figures tell the reader of your research how precisely you could measure your data. How precise was your measuring instrument? If you have more significant figures, you were able to accomplish a more precise measurement. With the rules for significant figures, remember that all non-zero numbers are always significant. That's easy. The tricky thing is, what do you do with zeros? Zeros are significant in two situations. If they are between any other significant figure, even if that zero is another zero, if they are between significant figures, they are significant. Or if the zero is both to the right of the decimal point, and sorry for this little typo, this should say of, to the right of the decimal point and at the end of a number, it is significant. So let's just go over a few examples with this zeros. If we have the number 1010, in this number there are three significant figures. The non-zero digits, of course, are significant, and this zero is found between them, so it also is significant. But this one at the end is not. If you have a number with zeros on the left end, as I talked in the video, such as a smaller decimal number, so here we have 0.0721. These zeros are not significant because, first of all, this one is to the left of the decimal point. This one is to the right of the decimal point, but it is not at the end of the number, so this number only has three significant figures. If there was a zero at the end, a trailing zero, it would be significant because it would be to the right and at the end of a number. You also need to know your rules for rounding off the answer to the correct number of significant figures. There are different rules for addition and subtraction as compared to multiplication and division. For addition and subtraction, the key rule is how many decimal places are existing in the numbers that you are adding or subtracting. You cannot have more preciseness in your answer than the least precise number that you were working with. So if you have a number that is going out to one decimal place, you're only allowed one decimal place in the answer, even if that number was very large and had 6 significant figures. You're looking at the decimal places available. For multiplication and division, you're looking at the total number of significant figures that are used in the two numbers that you are multiplying or dividing. And your answer cannot have more significant figures than the least number of one of the numbers for factors or quotients in the problem. So looking at these two specific examples, here we have an addition problem. This has the least precise measurement. It only has 2 decimal places as compared to 4 on each of the other two numbers that you are adding. So even though you can get this long number when you add them all together on your calculator, and you should work with numbers with more figures in them than are significant, you do the rounding off at the very end. But when we look at our answer, 24.6946, and turn it to the correct number of significant figures, we are only going to write 24.69 because there are only 2 decimal places in this particular number that we are adding, so there only can be 2 decimal places in our answer. We are rounding up, and of course the 4 next to the 9 would not cause that to increase. Moving on to the multiplication problem, we see that we have 4 significant figures in this number and 5 significant figures in this one. So we need to round our answer to 4 significant figures. Our 4th digit is a 5, so we need to and we look next door and find that it is going to be influenced by this 5. Remember, the rules with 5 are slightly different in science than it may have been in math class. It doesn't always round up. It rounds up if the number that it would be changing would be changed to an even number. It does nothing if the number is already even. So in this case, this 5 is not even, so that it would be rounded up to 30.86. If this number happened to be 30.84, the 5 next door would not have any impact on it. So remember, the rules for rounding up with a 5 is slightly different in science because we want to go up, round up sometimes, and do nothing some other times, so that it will average out more precisely than if we always round it up. You will also be asked to do calculations involving scientific notation. Remember, with scientific notation, you are looking at the exponents. 10 to a positive 3 is different than 10 to a negative 3. If we have a number of 6.72 times 10 to the 3, 10 to a positive 3, that means that the decimal point will be moving 3 places to the right if you're going to go for expanded notation, giving you a number of 6,720, or 6,720, no and should be said there. If we have the 6.72 times 10 to the negative 3, then of course we are going in the opposite direction with our decimal place, 3 places, and so the number that we have is 0.00672. So know how to work with expanded form or scientific notation form. Remember too that the format for your scientific notation is a number followed by a decimal point, followed by the rest of the significant figures, and then your 10 to whatever exponent. This 0 here at the end in the scientific notation makes it very clear that it is a significant figure because it is both to the right of the decimal point and at the end of the number. If we wrote out 4.770 times 10 to the 4th in the expanded notation, we would have 47,700. And in this format, it's very hard to tell if these zeros are significant because they are both at the end of the number. There is not a decimal point, and so at first glance, we would say both of these are not significant. But by writing the number in scientific notation, we can show that that first 0 is significant, that the precision of our measuring device was sufficient so that we could go out that many places. So that's where scientific notation can be helpful in showing that a 0 is significant, whereas writing the number in expanded form, it would be seen as not a significant figure. Then, of course, you'll need to work with the metric system. Remember, your metric system has a base unit. We've been working with at least fractions of meters and liters and grams with our triple beam balance. The key values that you need to know are the kilo at one end and the milli at the other with your base in the middle. And remember, I showed it as a stair step where you had 3 steps going in between the base and the kilo and down to the mila or milli. And so as you are moving, and it's oriented this way on this angle, so if you are moving from a base unit up to kilo, your decimal point will be moving to the left. If you're moving from a kilo down to a straight meter or liter or gram, your decimal place will be moving to the right. You also probably should put in your head that centi is right here above milli. You also want to remember that 1 milliliter is the same thing as 1 cubic centimeter, which also can be written as a cc. Thinking about all those doctor shows, if you watch those, and so that when you are given a problem that is talking about volume, you might be given the amount in milliliters or cubic centimeters, either as cc's or written out as centimeters cubed. I won't be asking you to do any temperature conversions on this test, but I do ask you to know the relationship between Celsius and Kelvin, or temperature conversions between Fahrenheit and Celsius. I will be asking you to think about converting between Celsius and Kelvin. Remember, the Celsius scale sets the freezing point of water at 0 and the boiling point of water at 100. Very, very hot. 212 degrees Fahrenheit, 100 degrees Celsius will burn you. And in between, of course, there are 100 units, 100 degree steps. And then the Kelvin scale came about because of a theoretical idea about absolute zero, a place where there is no kinetic energy. I can't spell this. Absolute. I can't talk and spell at the same time again here. Absolute zero, where there's no kinetic energy, there's no motion going on at all. And the units for Kelvin are exactly the same as Celsius, and the space between this absolute zero and 0 degrees of Celsius, where water freezes, is 273.15 either Celsius degrees or Kelvin units. Most of the time we just talk about 273. We don't worry about these two decimal places because we're not able to be that precise on our measurements. So know this distance here, this space between 0 on Kelvin and 0 on the Celsius scales. Have some idea about where 0 and 100 fits so far as how hot or how cold it is in sort of a comparison between the different scale systems. But no, you don't need to do temperature conversions between Celsius and Fahrenheit. Then we come to the naming of elements and making ionic and covalent compounds. You will need to be familiar with those required elements. I hope you've been memorizing what the atomic symbols stand for and how to spell those elements. Remember, in the periodic table you have two broad divisions between metals and nonmetals, and this is important when it comes to naming a compound. Remember that hydrogen, even though it's found over here on the left, is often a nonmetal, and so occasionally it falls in the role of a metal, but we won't really see that in this class until we get to some acids, so consider it a nonmetal, and that this division of between nonmetals and metals goes right past aluminum, which I think you can recognize as a metal. So you need to know those atomic symbols that have been required to be able to put the name to the symbol and vice versa, and you also need to know how to name compounds. So with ionic compounds, remember those are made of both a metal and a nonmetal, and you are listing the two parts to it. The first element is given its full element name, and that will be the metal. So the metal comes first, the positively charged ion always comes first, and then your nonmetal is the second half of the word, and you use the prefix, the first half of the name of that nonmetal, plus IDE as a suffix. So that if we have a compound that's made up of sodium and sulfur, then it becomes sodium sulfide in name. Or silver and oxygen becomes silver oxide in name. When it comes to our covalent compounds, then those are only can spell this right here today. Covalent compounds are only nonmetals. So we have a nonmetal plus another nonmetal. So it's only things found over here on the far right of the periodic table. And with your covalent compounds, the first thing listed will just have its full element name. And then the second thing will have the prefix for the name plus IDE, just the same as with the ionic compounds, but you use these special prefixes to determine or to indicate how many of each of the nonmetals is included. So you can look at these nonmetal covalent compounds, recognizing, because you know the atomic symbols, that we're dealing with nonmetals, and you can read off diphosphorus, hexaoxide, or dinitrogen tetrahydride, realizing that those prefixes only go on covalent compounds. Then you will need to do a little bit of math on the test, because you'll need to do some density calculations. Memorize this formula that density is equal to the mass divided by the volume, because I will not give that to you. You need to have that one memorized. So you have a problem that says the density of a metal is 2.12 grams per milliliter. So what would be the volume then if you had 45 grams of it? So here we've got our density equaling mass divided by volume. We can rearrange that formula to tell us that the volume is going to equal the mass divided by the density. And I know our book uses the symbol rho for density, but you can also just use a capital D if it makes more sense to you. So if we just plug in our numbers, our volume is going to equal 45 grams divided by the density, which is 2.12 grams per milliliter. And remember, this might be given not as milliliters, but as cubic centimeters. If you could go ahead and do the math, you'll find that that equals 21 milliliters. So a sample that is 45 grams in mass would occupy 21 milliliters. So you need to be able to use the equation for density to figure out either density or volume or mass of any particular sample. Even though I did not give you a quiz on using the law of definite proportions, this was something that you were asked to do in your textbook practice problems, so I hope you're comfortable with it because you will be asked to do it on the test. In this particular type of problem, we're using the law of conservation of mass to say that whatever goes into a reaction will come out of that reaction. And so we're reading here that 54 grams of aluminum plus 100 grams of sulfur made 150.3 grams of aluminum sulfide with some leftover sulfur. So this 100 grams of sulfur was in excess. There was too much. The question then asks you to calculate what amounts you need to make 100 grams with no leftovers. So nothing is in excess. You're doing this for chemistry industry. Nobody wants to buy chemicals they don't need, so we want to be precise about how much is needed. So first of all, we know that we made 150.3 grams, and we know we had 50 grams of aluminum. So if we take 150.3 and we subtract that 54 grams of aluminum, that'll tell us how much sulfur we used. We used 96.3 grams of sulfur. So that's the first thing you need to figure out. Then the next thing you need to do is figure out how much 150 needs to be reduced to get to 100 grams. So 150.3 grams times some decimal number, some fraction of decrease of proportion, will end up giving you 100 grams. How much are you decreasing it? This, of course, is going to be not a whole number, so it's not being decreased, by, or not being increased by 2, it's being decreased by something, by 0.5, by 0.2, by 0.3. We don't know. We have to figure this out. So if you solve for x, you find that the factor of decrease, just think about it maybe that way, is 0.6653. Remember, it is quite all right to keep more significant figures in your calculations than you will use in your answer. It leads to a more precise answer. So this is our factor of decrease. Then we just take that number and multiply it by the amounts that were used to produce the 150 grams, and it'll tell you how many you need to produce 100. So if we take over here, going back to our amount used originally, 54.0 times this factor of decrease, 0.6653. If you go ahead and do the math, I can tell you that you're going to use 35.9, that's a 9, sorry, grams of aluminum. And if we do the same thing for sulfur, if we take 96.3 grams of sulfur and multiply it by this factor of decrease, then we'll find out that in order to make our aluminum sulfide, we need 64.1 grams of sulfur. So make sure you can do these kinds of problems because they will be included on the test. And then finally, you will be asked some questions about physical and chemical changes. And the question you want to ask yourself is this matter permanently changed? If it is not permanently changed, if you can somehow reverse what has happened, or there may be a size difference, if you say crush a block of stone, in that would be an indication that it is a physical change. But if it is a permanent change, if it is something that cannot be undone or involves a chemical reaction, then it is a chemical change. So you need to be able to identify if a physical or chemical change is happening. And last, you need to be able to balance equations, and we went through this in class, so hopefully it's something you're feeling more comfortable with. You'll be given an equation like this one that says that sodium chlorate can be decomposed into sodium chloride and oxygen, and you need to figure out what is the coefficients. Remember, you are filling in this space in front of the molecule. You are never changing the subscript. So to do this, I suggest that you keep track of how many atoms you have on each side of the arrow. So over here we have 1 sodium, and we have 1 chloride, and we have 3 oxygen. And on the right-hand side, we have 1 sodium, and we have 1 chloride, and we have 2 oxygen. So obviously the oxygen is going to be the problem. With 3 oxygen in one side and 2 oxygen on the other, the way to handle this is to treat it like finding the common denominator in math, multiply those two numbers together, and then use that as the total you're going for. So 3 times 2 is 6. So how can we get 6 oxygen on the left? Well, we get 6 oxygen on the left by multiplying by 2. How do we get 6 oxygen on the right? We get that by multiplying by 3. So we've got 2 times these 3 oxygen, 6 on the left, 3 times these 2 oxygen, 6 on the right. But by adding a 2 over here, a coefficient on the left, we've also affected our sodium and our chloride. We've doubled the amount, so we have to put a 2 as the other coefficient here for our compound sodium chloride. And then the equation is balanced. So be sure you're comfortable then with all of the topics that have been covered in this video, because this gives you an overview of what will be on the test that you'll be taking at home this next week.